So today we're starting the first of two units that we're going to end the year with that are pretty difficult. This unit is kinetics and equilibrium. Kinetics, well, you might remember the word kinetic from kinetic energy, which is energy of motion. So keep in mind that kinetics has something to do with motion, and most specifically, we're going to be thinking about collisions. So I want you to be thinking about what we know about collisions in terms of pressure and concentration and all that as we go on. Let's review what is a chemical reaction. And I've often used the toy of Legos to represent a chemical reaction because before you can make something with Legos, you first have to take the Lego pieces apart from the project that someone else has made and recombine them. And if you remember from the energy unit that we learned that it always takes energy to take those Lego pieces apart, which is to break bonds. Well, what determines how fast a reaction is going to go? It's not just instantaneous. Like you have reactants and bam, it turns into product. Just like with Legos, you have to take some time to take the pieces apart and recombine them. And what determines how fast it's going to go? Well, how much rearranging has to occur and how much surface area is there where they touch. So the more places where these molecules are touching each other and can react, the better it's going to be. So how often they collide and just how effective those collisions are will determine how fast a reaction is going to go. So how do we measure that, how fast a reaction goes? Well, just like with anything else, we call it's in with a rate, which is how much it changes over time. So if you think about a reaction, so we have reactant molecules just to start, and then the reaction goes, and we have some products starting to form. But again, it doesn't happen instantaneously. We have to have each of those molecules need to collide and rearrange, and as time goes on, more and more reactants are going to disappear and more products are going to form until all the reactants have reacted and all the products are available. So what would be some things that influence how fast a reaction goes? Well, hopefully you can figure this out for yourselves, but since you're not here, I'm going to tell you temperature affects it because what do we know about temperature? Temperature is average kinetic energy, so the higher the temperature, the faster particles are going. Concentration affects rate because if you have more particles per liter, there's going to be less space and there's going to be more collisions. Catalysts, we can see why that influences a chemical reaction as we look at the potential energy diagram here in a minute, as well as inhibitor. Surface area, as I showed you with that light bulb picture, shows that the more places that molecules are touching each other, the more chance there is for effective collisions. Pressure is obvious, right? Because we learned that pressure, the definition of pressure is a number of collisions. So the greater the pressure, the more collisions there are, and the faster the reaction is going to go. And as we said before, how much rearranging actually has to occur for the products to form. So what is a reaction mechanism? Again, the world probably thinks you have these reactants and then as if by magic, bam, all of a sudden you have products. But that doesn't happen like that. What happens is that one thing forms and then that turns into another thing and another and another. And those series of steps are what we call the reaction mechanism. Now, most of those things that form along the way, we don't even know. They happen so quickly that we can't even see what they are. But the intermediate that takes the most energy to form is what we call the activated complex. And from the energy unit, we know that when you're looking at a potential energy diagram, the energy that it takes to go from the reactants to the activated complex is called the activation energy. So let's take a look at what we've learned before about potential energy diagrams. If you have a reaction, it always is going to take energy to get the party started. We need to take those pieces apart. We need to form something in the middle. That which takes the most energy to form is called the activated complex. So some other definitions we learned is that the difference between the reactants and the top of the hump, which is the energy of the activated complex, is called the activation energy. So in this unit, we're going to be studying that some reactions can even go backwards. And we're going to be learning about that when we start talking about equilibrium. So if you imagine this potential energy diagram and picture going in the reverse direction, the activation energy on this picture is represented by the red arrow, the red top arrow. And then also a review, we learned that the change in energy, or delta H, is the difference between reactants and products. One way it's positive and the other way it's negative. All right, what I want you to do is I want you to think about what all the different things that we talked about would be ways to speed up a reaction, and think about effective collision. So let's talk about some scenarios. A boy and a girl molecule are walking on the beach in opposite directions. The girl is walking with her feet in the water. The boy is about 10 feet farther up the beach. Does this make for good chemistry? And again, you're thinking about effective collisions. Well, hopefully you recognize that they're too far apart to really have a good effective collision. In scenario number 2, we have these two students that are walking. This time there's a shark attack in the water, and they're both watching as they walk, not paying attention to where they are walking. This time they collide, but it's a big mess. His foot ends up kicking her in the face, and she elbows him in the stomach. Does this make for good chemistry? Well, hopefully you recognize that if they want to kiss, they need to be lip to lip. And with this craziness that they're falling on top of each other, they really can't make for an effective collision. In scenario number 3, this poor girl, she just ran a marathon. She's pooped. What does she feel like now? They're walking straight towards each other, but this time they collide in the correct orientation, face first, lining up properly, but she doesn't have enough energy. Does this make for good chemistry? And then finally, they each just ate a power bar, so they have lots of energy. They each drank some Red Bull. They're walking straight towards each other, colliding face first, lining up properly. Does this make for good chemistry? And I hope that you can recognize that they have enough energy and the correct orientation to have a proper kiss go off. So as we do kinetics, it's going to get more complicated this week, but the more that you can understand about everything we're talking about in terms of collisions, sometimes kinetics is called collision theory, the better you will be.